What have we been studying in this past chapter? Glycolysis. And glycolysis is how we begin to study what? Metabolism. And metabolism for the big picture is what? We use metabolism. I have a slow metabolism, right? What is that? What does it actually mean? Breaking things down. And a lot of times we learn metabolism in terms of the food sources that we begin to eat. That's carbohydrates, fats, and proteins. And we do break them down, hopefully, to create energy and to have the starting material to synthesize all the different biological molecules that we need. But metabolism also includes synthetic processes by which we take in things and convert them into other things. And so there is a balance of all of these molecules that come in. Now, metabolism is taught in terms of pathways. And we just learned one pathway, glycolysis. There were 10 different structures, starting with the sugar glucose, right here. Okay, and this is one of the different ways that we can draw glucose. And glucose was converted into what? What was the first conversion? Glucose becomes glucose what? 6-phosphate, right there. Okay, and so there's glucose 6-phosphate. What actually did that? Oh my goodness, there is a number, 3.1.3.9. Remember the enzyme names, and they can be classified in the systematic way. They're given a number and subnumbers. What was the enzyme name that we talked about for glucose to glucose 6-phosphate? Hexokinase, right? And so if I go over to, let's see, the side, and there's the ones, and there's still ones, and there's some twos, and there, over the twos. Okay, and wait a minute, there's some threes. Oh man, it was a 3-1 something. 3-1, 3-9. Nope, that's not that one. The arrow was the reverse. Oh man, totally messed up. Okay, that was the reverse reaction. Okay, oh no, now let's find it back there. Oh yeah, that's where I'm getting to. Okay, so, the 3-1-3-9 goes up to glucose. We wanted to go down, which is, 2-7-1-2 and 2-7-1-1. Okay. 2 4s, 2-7-1-1 and 1-2. 1-1 is hexokinase, and 1-2 is glucokinase. We learned both of those. Okay. I have no idea where I'm at. Where am I? Okay, there it is. Glucose. Glucose 6. We learned that. Glucose 6 went to fructose 6. Fructose went to fructose 1,6-bisphosphate. All right. And so this is the pathway that we learned. All right, glycolysis. So let's see if we can see all of glycolysis. Glucose, resolving. Glucose up here at the top. Glucose, that's fructose. Okay. All right. Glyceraldehyde. All right. 1,3-bis phosphoglycerate. 3-phosphoglycerate. 2-phosphoglycerate. Phosphoenol pyruvate is down here. Pyruvate, there's it. Starting at the top and going to the bottom is glycolysis. It's the middle. But as we learn new pathways, this is just like a roadmap. They can go to different pathways. Now, what we are going to learn is metabolism. Okay? And we're going to learn and look at almost every single reaction as we go through, because they're all important.
Wait, like for the rest of the year or like for this semester?
Oh, we'll probably hit about 80% this semester.
Where can we find this
Ah, this picture, I can actually put it on Moodle. I don't think I've ever have, but I will. And if you go into my office, behind my desk is a printout of this. I have hanging. It just keeps me reminded of what I have to teach. Okay? And so, when we start up the next chapter and we overview what the chapter does and the book does, it simplifies it for you. Okay? And here is glycolysis, that pathway. Okay?
That's so much fun.
You can handle this one?
Yes.
Okay? And there are glycolysis connects how we deal with carbohydrates, and we actually looked at a little bit of the carbohydrates about how sucrose and lactose came in. There was a little bit of how we had to manipulate the sugars to get it into glycotic intermediates. All right? And then as we finish up glycolysis, the next cycle that we run into is the citric acid cycle, and that's what this chapter is. But we're also going to connect that to how citric acid cycle will be connected to fats, and look, arrowheads both ways, and how citric acid cycle is connected to amino acids, both degradative and synthetic. And we can go up to the nucleotide synthesis, because those are important things in the body too. And then oxidative phosphorylation. And then we do a compare-contrast to photosynthesis, because that's another way in which ATP is synthesized. So what we're trying to do is we will learn one path. Know it, love it, learn it. Because we'll learn another path. We'll know it, love it, learn it. But what we're also going to need to do is conceive how they work together. Because the body has, just like you have the ability to drive from here to Chattanooga. Okay? You could choose to take I-75 south and go to Chattanooga. Or you can take I-75 north, go to Knoxville, I-40 west, go to Nashville, I-24 south, going down to Chattanooga. It'll get you to Chattanooga, but it's a whole different pathway. And that's what we're going to look like. Sometimes, just like traffic, in metabolism, some of the pathways get backed up, like trying to drive through Atlanta any time of day. Okay? It just gets backed up. And so sometimes you have to take an alternative pathway to get to where you need to go. And that's how metabolism will work. We will also try to keep the balance of all the different concentrations controlled to a level that is set by homeostasis. Okay? And if you perturb the system, either by using up too much energy without replenishing, or you eat, you get everything out of balance until it works its magic and gets it back to the right concentrations for all of these different intermediates. And so we'll learn the transformations, we'll learn the regulation about how these work, and then we'll decide if the body is under this condition with this, how might it work? And so can it go the way that you want it to go? Maybe not. I might have to go around a different way. And so I want to get you to be able to think through that. But first, we have to learn the basic pathways. Okay? Citric acid cycle, all right, is a mode of oxidative degradation, all right, aka also known as the tricarboxylic acid cycle or the Krebs cycle. Why the Krebs cycle? Dr. Krebs worked on it. Okay? Now, citric acid cycle is both a catabolic or degradative and an anabolic or biosynthetic pathway. And so there are a lot of arrows coming in and out, and the citric acid cycle is just like a traffic circle. I hate writing in those because nobody knows how to use them, all right? But it is central to being able to go to a lot of different places. And so we're going to come in and out of the citric acid cycle from this point on, and we will need to understand where we are in any pathway. And so sometimes we take things from the citric acid cycle, sometimes we run them through and allow everything to be degraded. All right. At the end of the citric acid cycle, we'll have a couple things. We'll have CO2 as a product. Okay. We will also have lots and lots of electron carriers because this is an oxidative process. And if anything oxidizes, we have to reduce. And so we are going to convert the energy at the end of glycolysis into another form of energy, or pools, concentrations of energy. Where is all of the energy, the potential energy, left at the end of glycolysis? There were three things that we said. Pyruvate was one, ATP and NADH. So those are the pools. ATP is at what we think is the end one, but the NADH can be converted eventually into ATP, and the pruvates can be converted into ATP. Now, biological redox types of reactions can have electrons move from metal centers, and we can have oxidation reduction directly. We can reduce things by adding hydrogen atoms with electrons. We can react with oxygen directly, but a lot of times, mechanistically, we are going to have hydrides move. Okay? A hydride can be a leaving group in biological systems because we have an enzyme and we have an acceptor. Okay, an electron acceptor. It is very difficult and highly energetic to have a hydride leave in an organic flask. It takes a lot of energy, but the enzyme allows this to happen very easily in biological systems. Now, if I go way back to GChem2, oh man, GChem2, that's like a horror statement, right? We learned how to calculate energies based upon redox, and if we actually take a look at the electron potential, we can take the half reactions. We can take the acceptor potential minus the donor and get a delta E, place it in the Nernst equation that has a funky little constant, which I will give you, and we can calculate the delta G for reaction. And what really messes people up on this is people don't remember this one right here. N represents the number of electrons that are moving, and almost all of the time we are going to have 2 electrons move, and so everybody's answer comes exactly 1/2 of what it should be. And that is the first choice A on any multiple choice, right? Very simply, if I look at the reaction pyruvate plus NADH plus proton creates lactate plus NAD, because I give you the half reactions, you really didn't need to know what the reaction was, but you can take those two potentials and you can potentially calculate a delta G. I would bring a calculator to the exam. All right. There are 2 main electron acceptors that we use in these processes. One is NAD+, okay, and that is used in the citric acid cycle. There is an NADP+ that exists, and the difference between an NAD and an NADP is if you have a phosphate right there. Okay, the rest of the molecule is different. Although that phosphate is really, really important. The NAD that has no phosphate is used exclusively for degradation. If you put that phosphate on the bottom, it doesn't fit into degradative enzymes at all. It fits into synthetic enzymes. So that one modification directs whether I donate a hydride or I accept a hydride. I accept a hydride in degradation. I donate a hydride in synthetic processes. Okay? Now, where in the world does the hydride actually react? All right? I wish I could see this better. Okay, so I'm going to redraw this, and I'll show you where I'm going to redraw. I'm going to redraw this right here so that you can see it just a little bit better. Okay? Maybe it printed out well on your slides. Maybe it didn't. All right. Some things when I look at this. Make sure I have everything out. I'm just going to put R there just for convenience. I'm going to put H there. Okay, and I'm going to put a plus. Okay. The nitrogen is positively charged. all right, in the form that can accept a hydride. That's where the NAD plus comes from, all right. When you have a hydride that comes in, so this is a hydride that is leaving something and is going to be accepted by this. This is what happens. I come in and attack right at the top of the ring. The electron pairs, okay, will form a double bond here, and this electron pair will then sit on the nitrogen. Okay, I will get an intermediate that looks like this. 6-membered ring with a nitrogen, a lone pair, double bond, and 2 hydrogens with an R group. Very stable, okay, in terms of once it accepts that hydride, I was positive, now I'm neutral. So it is very easy to accept that particular hydride and carry it along. I can reverse the reaction by taking this pair of electrons, form back this pair of electrons, reform, and the hydride can fall off if it needed to. Okay, and I'm going to allow those electrons to move eventually, okay, and so it's at the top by which it accepts. All right, one thing I need to point out to you about the structure. All right, here, adenine, the ribose sugar, 1 phosphate, 2 phosphates. What does adenine, ribose, phosphate make? Give me an acronym. ADP. ADP is a fundamental part of the structure. In actuality, the organic structure at the top is one of the vitamin Bs, that organic structure that accepts the hydride. All right?
So the thing you redrew is
Is one of the vitamin Bs. I can't exactly remember which one, 5, 2, 12, whatever, one of those. Okay? Okay, take a look at this experiment here. A lot of times we track either the production or the use of NADH, converting to NAD plus, okay? And we do this using a absorbance in the UV range. And so, what wavelength, if you were going to set up an experiment, would you use to determine either the increase or the decrease of the reactant to follow the progression of the reaction? Because as you go through the reaction, it's either going to be used all up or made from nothing. What absorption wavelength might you choose based upon the graphs of the absorbances between those two substances? 260 is okay, 260 is a place that would be absolutely one I might do, okay, because that gives the largest absorbance. But to tell the difference between how much NAD plus and how much NADH is there, I would only have between here and there. And then how do you distribute it? If it comes right between, how much of the H do you have and how much of the plus do you have? Is there any better place to choose? 340. 340 doesn't have as good an absorption. So most people actually select the highest, and that's what we try to do. This does not have the highest absorption, but it has the best place to distinguish. Because if you are all NAD+, you have no absorption. And if you have the NADH, you actually start to have absorption. And so it can be done at 260. It is very complex to discriminate. But at 340, it's much easier to discriminate. And it actually has a more sensitivity because it's a larger difference between the two. And so if you take a look at experiments And if you read the methods section and you're ever following either the production or the use of this, they will tell you to use absorption at 340. Okay, so most of the time you don't actually have to develop the experiment. You just read what somebody else did and repeat. Okay, the other acceptor is FAD, which becomes FADH2. Okay, so that's weird because NAD plus accepted a hydride, right? And it had NADH, right? Accepted one. This one, I accept one hydride and I become NADH2. And everybody asks what? Where does it get the other one? Okay, let's look. All right, FAD structure. Oh, wait a minute. Adenine, right? Ribose. Phosphate, phosphate. What is that structure? ADP, okay. And then an organic structure. All right, in the final product, here is the reduced FAD, becoming FADH2. All right. I will have two possibilities. Watch. Dun, 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 dun. I'm going to do blue hydride. It could attack here. It could take this pair of electrons and form the double bond there. And it could then pick up a, oh, this is great. I'm not going to put a proton. Okay. One possibility. Second possibility, the red hydride, okay, could attack at the top, nitrogen. The electrons now kick to form the double bond, and now this bond picks up a proton. Both arrow movements, the blue and the red, will form the FADH2. The reason why the second hydrogen is picked up, and this is a proton, is after this electron movement, the nitrogen can become negatively charged for a moment, and that is so basic, it picks up a proton. Or after these attack, this becomes negative, it picks up a proton. That's where the second one comes in. All right. Find a neighbor, talk to them. Which one normally happens, red or blue? Say? Oh, the semiquinone, it's one electron. It's in the middle of the process, and it picked up one electron and then a second electron. So it can carry one. It normally carries two. It has the ability to carry one. All right. How many, by show of hands, say that your neighbor said it was blue? Okay. I've got one person, two people, well, two halves, so that makes one. All right. How many says their neighbor said it was red? Okay, there's a lot of red here. Okay. Why would anybody say that it's red? Sterics. Okay. The top of the ring structure is much, much more open than the bottom because the rest of that organic chain would be sterically hindering of something attacking. So if we predicted it should be the top, but the enzyme will actually place the reactants together and cause the reaction to happen, it does happen at the top almost all of the time. Organically, the resonance structures and the intermediates are exactly the same. So if I top the bottom or the top, organically the movement of electrons really has no play in it. It's all about the sterics. Okay. So we now have a couple of electron carriers. We're going to use both of those in the process. All right. We have done glycolysis in the cytosol. Okay. The citric acid cycle occurs in the mitochondria. Describe the mitochondria, if you have to give it a definition. The powerhouse of the cell. Yes, it is the powerhouse of the cell. Okay? A lot of processes do occur, mainly the inside of it, the citric acid cycle, and then inside the membranes we're going to have both the flow of electrons to create a proton gradient and then the synthesis of ATP. But to get there, we've got to get all of the material, the pyruvate, from the cytosol into the mitochondria. Okay? To do this, we have to power it. Okay? What does symport mean? They both go in at the same time through a protein that is a transporter. Okay? So a pyruvate will come in with a proton into the mitochondria. Now, the mitochondria tends to have a lot of pyruvate inside of it. So pyruvate is going up a gradient, but the protons are going down a gradient because there's usually lots of protons on the outside. So this is an active transport to get the pyruvate inside the compartment by which I can do the next set of reactions. Okay? So once inside the matrix, there is a one-step reaction. Well, it looks like one step. That converts pyruvate into the starting material of the citric acid cycle. So this is like a one-step pathway, okay? And the enzyme that does this is the pyruvate dehydrogenase complex, and that's a wonderful name for what we're going to see it, okay? And it converts pyruvate into the entity called acetyl-CoA. All right. What name, enzymatic name, do you see there in this enzyme that makes you kind of classify it into some sort of classification scheme? The dehydrogenase. We've seen dehydrogenases before. Dehydrogenases have hydrides moving or as leaving groups. It also requires a cofactor of either NAD plus or FAD to accept the electron or an electron acceptor. And so when you look at your list of enzymes and you see dehydrogenase, okay, mechanism will have a hydride leave and a cofactor of an electron acceptor. Examples, NAD plus, FAD. Okay, the pyruvate dehydrogenase complex is actually a whole bunch of enzymes, 3 to be exact, 3 different kinds: pyruvate dehydrogenase, dihydrolipolyl transacetylase, and dihydrolipolyl dehydrogenase. Oh my goodness gracious, if you could say that one time slow, I'll be proud of you. All right? It consists of 60 proteins working together. The size of it is 5 million Daltons. Oh my goodness. I know Dalton, that's just down the road. What in the world does a Dalton mean? Have you ever heard that term? I've heard it. Did you ever understand what that term meant? No? Okay, you probably heard it as kilodaltons. We use it with protein sizes. A Dalton can be substituted for grams per mole. Okay, it's its molecular weight. To weigh out a mole of this complex, you would have to have 5 million grams. That's a lot. It's big. Okay, and it's actually ordered, and it looks geometric. So that's kind of weird. Why would a protein look geometric? But what happens is, having all of those together, this is a fundamental reaction that has to go very quickly, and so being in the complex increases the speed of the reaction. All right. Before we actually look at the enzymes themselves, we have to have some cofactors. Now, I described a couple of cofactors for you already. NAD plus and FAD. Okay, those are cofactors that are required. Okay, the next cofactor that I'm introducing is called TPP, thiamine pyrophosphate. Have you ever heard of thiamine? That's another vitamin B. Okay, and the thiamine pyrophosphate is this really strange organic molecule here, and we're going to see what it does in a moment in terms of the mechanistic part of the reaction, but I have to have this to do the reaction. Okay, the next item I'm going to look at is lipamide. Lipamide is kind of oddball. It's a 5-membered ring that has a disulfide bond, or 2 sulfurs bound together. It's got this long chain, and by itself, it actually has an acid, but that's not an acid. How the lipamide is attached to the protein, and so here's the peptide chain of one of the proteins that are in this complex. It has a lysine. The N-terminus lysine on the R group reacts with the acid to create a peptide bond, or in organic chemistry, we'd call that an amide. And what happens is you've got this functional group on this long chain that is a single bonds, and so really it's this long flippy thing that kind of can move. What we're going to do is we're going to take this lipamide, do a reaction on one side in an active site of one enzyme, put something on it, and then it'll flip over directly to the other enzyme carrying the reactant, and it goes back and forth. This increases how fast the substrate gets from one enzyme to the other. Okay? So that is its function. The last is coenzyme A. Okay? CoA we use, or we use CoA with a -S-H. All right? We write CoA, and here's an example of how we write it a lot of times. This has an acetyl group, there's the acetyl group, attached to a CoA. That looks really tiny, okay? But this is CoA. There is the SH, okay? Here's an organic linker, and then, oh, wait a minute, what is this? Adenine, and a ribose, and a phosphate. What does that make? ADP. It sure seems like ADP is a fundamental structure that's happening a lot, okay? And so what we don't show is this big structure all the time, but it's huge, okay? We usually abbreviate it because we're scientists and we're lazy, okay? But what's important about the CoA, anything attached to a CoA tends to bind to enzymes that break things down. It's kind of like an address book to go to enzymes that break things down. All right, so here's the process. All right, pyruvate. This looks weird, but watch this. Pyruvate will first react with TPP. This is a cofactor inside the enzyme. I'm going to deprotonate that proton having a negative charge. It will be a nucleophile, and it will attack this ketone, and this acid right here, you're going to have electrons kick down, and CO2 is going to fall off. Okay? If we combust a hydrocarbon, we make two things. What? GChem1, combustion of a hydrocarbon. CO2 and H2O. You are combusting hydrocarbons, sugars, in this process. Here's the first waste product, CO2. Okay? I have 2 carbons attached to this cofactor. Okay? This cofactor will then react with the lipamide. And I transfer these 2 carbons plus that oxygen onto one of the sulfurs. So I have 2 carbons that originally were these 2 carbons. I then react this with CoA, and CoA has a sulfur, and so I substitute this sulfur, that carbon bond, to the CoA sulfur and that carbon bond. And now I have a dihydrolipamide that was once connected and now not connected. Or we can say reduced and oxidized. Okay? The enzyme stops at this point in time if I can't do something. If I can't take these electrons and oxidize them back here, I can't go. But if I have an FAD, I can accept the hydride. But this FAD never leaves the enzyme. An NAD that is mobile in the liquid can come up, take the electrons from FAD, and send them off as an NADH to carry the electrons away. And so you never see FAD in the overall reaction because it's never kind of leaves, but we do see NADH. What's really happening here is the enzymes will be differentiated in that the connection over here carries your two carbons, does a reaction, puts it on, and then it will move over and it will do the second reaction. All right. To actually look at what the mechanism looks like, all right, we'll deprotonate the TPP. It will attack at the carbonyl because the intermediate is negative. It attacks the partially positive carbon. And we saw before that when you attack a carbonyl, there are two things that can happen. I can kick up and I can kick down. Okay? Or the second, if I attack it, I can kick up and pick up a proton and become a hydroxide. Those are the two things that you know that can happen if I attack a carbonyl. In this case, I will have the hydroxide attack. All right? Now, all that to get the CO2 off. This organic structure here is going to allow us to create an intermediate so the CO2 can come off. Watch. The electrons on this atom will fall in. Now, all right, let's go back to G-Chem. What is the Lewis structure of carbon dioxide? What are the steps to draw a Lewis structure? What is a Lewis structure? Yeah, you got to figure out how many electrons you have, right? And you have to pick the central atom. You put one atom, the outer atoms around. You fill octet, and then you make sure the central atom is full. I won't do that because I know what this is. Here's CO2, right? Okay. If you take a look at the acid, that negative charge is representing a lone pair of electrons. It is almost just like a CO2, right? If I take this pair of electrons and put them there, I get a double bond. I have two lone pairs, right? All I have to do is get rid of these pair of electrons. That's the hard part, that pair of electrons wanting to fall away. Because I have this organic structure attached, these electrons fall in to form a double bond. This double bond fits onto that nitrogen that has a positive charge. When this goes on here, what charge does that nitrogen now have? Neutral. That is why organically this reaction is stable, is because that organic structure is there. Okay? Now, that's all well and good, okay? And, sorry, you should have a resonance structure here, a resonance arrow. Okay, well, now I've really messed up the arrow. Okay. All right, and so there is a resonance structure that has the negative charge sitting on the carbon. What is that called? Carbanion. Tell me energetically, stable, unstable? Unstable, very unstable, okay? Carbons are not electronegative. Having a negative charge is really, really bad, okay? So in the resonance, it's like 99% here because that is a whole lot more stable, right? But this doesn't react. The 1% that gets here does the next reaction. Once it reacts, attacks the sulfur, and the sulfur picks up the proton, I have 0%, and so what happens? I distribute. And then I react, I distribute. And I can drive that reaction, even though the equilibrium isn't really great, I can drive the reaction to completion. Okay? So now I've got the TPP, and after this I've got the lipimide all bound up together. looks a little crowded. That really looks nastily crowded there, okay? So what I'm going to do is take a base, deprotonate the hydroxide, create the ketone, and the lipamide, which this was the active reaction that started, comes off in the enzyme, and it's ready to do its next reaction. But I now have this ketone with this methyl group sitting on the lipamide. This is where the lipamide swings over to the other enzyme. The next reaction, I deprotonate the CoA. The sulfur will attack at the CO2, not the CO2, at the carbonyl. Electrons kick up, and here's the other thing, can kick down, and this is a leaving group. I now have the acetyl-CoA, which will then go to the citric acid cycle. But I have a dead enzyme unless I do the oxidation here. Base, take one of the protons, I will attack the other sulfur. An electron pair will, or a hydride, will be accepted by the FAD. This is my crazy FADH2. I deprotonate that, and one falls off as a hydride to NAD plus to become the NADH. Okay, so that is the mechanistic steps for the pyruvate dehydrogenase complex. It is complex. All right, all that to get CoA. All right. Acetyl-CoA is at the top. That used to be pyruvate. These are the reactions of the citric acid cycle. In this particular version, I do provide one intermediate that doesn't leave the enzyme, but I show it for clarity. And so you see a 2A and a 2B in this process. And so we will do 1, we'll call that 2, 3, 4, 5, 6, 7, 8 reactions to complete the citric acid cycle. All right. In that, I have 2 carbons coming in, right? As I go through the reaction, check what comes off. What's that? CO2. And then what's that? CO2. And so I start off with 2 carbons and 1, 2, 3, 4. 2 plus 4. Good, you didn't even get out your calculator. All right, 6, 6, 6, 5, 4, 4, 4, 4, 4. Okay? And so I added 2 carbons, lost 2 carbons. And here's the CO2s that are produced, and that means 1 pyruvate equivalent, did you hear me? 1 pyruvate equivalent has been completely oxidized to carbon dioxide. Carbon dioxide is a carbon entity I cannot extract any more energy from. I've extracted all the energy from that. I have now created energy in the form of electron carriers, both lots of NADHs and some NADH, and I'm going to make specifically a GTP, which everybody and their brother says is just another ATP, because I can transfer that phosphate between the two without loss of energy. Okay? And so, these are the reactions. First reaction. The molecule oxaloacetate plus acetyl-CoA plus water will equal citrate plus proton plus CoA. The enzyme's name is a citrate synthase. A synthase is going to create a bond between 2 entities without the use of ATP to power it. All right? And so, if you take a look at this, all right, if by chance I made you come up here and draw this mechanism, all right, 1, you would be absolutely terrified, right? Okay, but 2, what, besides crying, would be your first step in trying to figure out what in the world happened? What? Figure out what's different. What else? Yes, you always draw a base because it's all about the... Okay. All right. That is very important. All right, so you can see what changes. And then in something this complex, I tend to like to try to inventory. Okay, so I'm going to do red, 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 red. And I'm going to do not green because I'm red-green colorblind. Blue, blue. Okay. And so, what do you think this atom would be, red or blue? It's got a ketone, blue, and it's got the CoA. That's that one. So if that's blue, what does that make this one? Blue. And then the others must be red, 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 and red. You got to find it. Red. Reminds me, what's your favorite Kool-Aid flavor? My Kool-Aid flavor is red. Okay. All right. So now I've identified things. Do you see any carbon that has a difference? Which carbon has a difference? Or what is a difference? One has how many protons? 3, and one has 2. Here it has 3. Here it has 2. All right. Now, what's the difference in the red? Where was the change? What did I lose in the reactant? A ketone, and it became a what? Hydroxide. Okay. So that means the blue one there and the red one there have to come together. Okay. If I drew a base in no particular place on this slide. Okay. All right. I have to take off a proton, right? Now, which one of the 3 do I select? What? What? I think you got the answer. Go ahead. It doesn't matter. Yeah. It's all equivalent. Good. All right. Now, why is that proton, any one of those protons, acidic? They are actually slightly acidic. Do you know why? What is it? Not just the charge of the oxygen. It is the electronegativity. What happens is the intermediate will have a negative charge on a carbon. That doesn't seem good, but that negative charge could form a double bond, and then the negative charge can be on an oxygen. Negative charges on an oxygen, not great, but okay, much, much more stable. And so it can form a resonance structure. So these protons are actually acidic. All right. Now, going into that resonance structure doesn't help us, but a negative atom can be a nucleophile. And nucleophiles like to find an electrophile. And what is an electrophile in the reactant? Which atom? The carbon. An electrophile is something that is positive or partially positive, and because of the carbonyl, the carbon is partially positive. So I will attack the carbonyl. All right, at this moment in time, you have 2 choices. I can kick up and kick down when I attack a carbonyl, or I can kick up and pick up a proton. What am I going to do? Kick up and grab a proton. The reason is here it has to be a hydroxide. And that's the reason why I do that. All right. That is not citrate. This is an intermediate, right? What has to happen for citrate to actually form? The water has to react, and what has to come off? CoA. Okay. I do that by doing this. Boom. Take off that. The hydroxide, a nucleophile, will attack the carbonyl. I will then do what? When I attack a carbonyl, what do I have to do? Kick up. Then I will kick down because I have a ketone here, I have a ketone there. That's why I have to kick down. And then I have to have a leaving group, and that will be CoA that picks up a proton. as the leaving group. I now have citrate. One of the names of this cycle is the tricarboxylic acid cycle. Why? What? There are 3 acids right here in citrate, 3 carboxylic acids. Now, 2 of them drawn differently, right? This in the traditional kind of quick form, and then these 2 articulated. Okay. And so, that's cool. Synthase. Yes. Aha. Very good. All right. What I drew in the reactant is not the product of what I drew in the mechanism. Up at the top, it should have looked like this, correct? Should have looked like that. Okay. Now, what are the pKa's of acids in general? Do you know? It's a numerical value. You may or may not know. Okay. Most acids, organic acids, have a pKa of about 4. Okay. And so when this is released into the solution, there's a buffering system that has a pH of about 7. And if you are either above more than 1 unit value or below more than 1 unit value, you're either protonated or deprotonated, depending upon the pKa state. And so once this is released, just because of its inherent pKa and the buffering system, it will be deprotonated. Okay? And so a lot of times you will have a deprotonated or protonated form, and it comes back to whatever you produced has a certain pKa and there's a certain pH value. And so that was a really good question because a lot of people get confused about that. All right. Citrate synthase catalyzes the reaction between acetyl-CoA and oxaloacetate. What's interesting is the oxaloacetate has to bind first to the enzyme because there's no binding site for acetyl-CoA. It only creates the binding site when the protein and the second substrate, the oxaloacetate, is there. Okay? And that actually causes the reaction to occur. There are 2 histidines and 1 aspartate that play important roles. Let's go back for just a moment. Here, I needed a base. Here, I needed a base. Here, I needed an acid. Between the histidines, 2 of them, and the aspartate, 2 of them act as bases, and 1 of them acts as the acid donate. Okay? Because I bind inside, I only react one way. Okay? And it proceeds through this reaction. All right. This reaction here goes from citrate to isocitrate. Iconitase. Now, this particular enzyme doesn't give you a good, it's not systematic name, so it doesn't give you a good idea of what class it is part of. Okay? And so, in this particular reaction, all right, I am going to go from this structure here, because this carbon changed, that carbon changed. Okay? Can anybody from your extensive organic knowledge tell me what kind of reaction from here to here happens? It's a very simple one, yes. When you create a double bond, it is a enol. No, this is not an enol, but it's close. Okay, the mechanism is going to be this. E2, if you can remember. It's an elimination reaction. Okay? And it is much simpler than you think. All right, do you see something that has too many protons? Yeah, one of the methylene at the bottom has too many protons. Base takes that. Those spare electrons form the double bond, and that will pick up a proton. Water leaves. Now what happens? I'm going to hydrate it. I'm going to add water across that double bond. All right? But to add water, what happens is this carbon now has a hydroxide attached to it. How do I change a water into a hydroxide? You take a base and you deprotonate that. This will attack at that carbon. Why does it attack at that carbon? Okay, here's the simple answer. The enzyme optimizes those two atoms to be right next to each other. The enzyme forces it to react there. Okay, and then this picks up a proton. And I get isocitrate. What's the difference between citrate and isocitrate? The location of the hydroxide. That's it. All right. Okay. The next enzyme is isocitrate dehydrogenase. Okay. This is called a. This is going to be a oxidative decarboxylation. Okay. So oxidative decarboxylation, well, oxidative is one reaction and decarboxylation is a second reaction. So I got two reactions jammed into this one. Okay. And if I have a dehydrogenase, I know I'm going to have a hydride leaving. And so I am going to need an electron acceptor in here, NAD+. All right, do you see where the reaction occurs around? Can you see the difference? Best thing is to try to look in inventory, exactly the same, a little bit different. Okay. All right. So in a dehydrogenase, if you wrote in your little chart, you're going to deprotonate and then have a hydride leave. Okay? And then the hydride is accepted by a cofactor. So I have a choice. Okay? I have a choice of proton 1 or proton Z. Which do you think might be the one that is easier for the enzyme to deprotonate? 1 or Z? 1? Why? Yes. If I deprotonate 1, the negative electrons could potentially be on the oxygen for just a moment in time. Negative charge on the oxygen, okay. If I take Z off, where are the electrons on? A carbon. Not as happy. So I would predict that it takes that and deprotonates that one. This pair of electrons forms the ketone, and this is the hydride that falls off onto the NAD+. Okay. All right. Now, because I have the ketone, I now have a reason why the CO2 will fall off. Last time, how did a CO2 fall off? What electron movement caused the CO2? What was the beginning movement? We just did it. You know, 92% of the time you're going to deprotonate something to do a reaction. This one's not a deprotonation. We took what? Okay, I'll show you. We're going to take this lone pair and form the double bond. But the hard part is the next electron movement. Okay? If by chance I just have to put that carbon, that negative charge on a carbon, it doesn't like to go. So I have to have something else to work it. Because I have this ketone now, I do have something else to work. See a double bond here and an alcohol? Once this pair of electrons falls in, that pair of electrons has to go somewhere. It's going to go there to form the double bond, which then allows this to pick up a proton. This intermediate is stable because it has no additional charge. Yes? Oh, could it resonate up? Yes, it could have. And in most cases, the acids are resonating all the time. And so, yeah, and whenever you see an acid, I have to pick one because I want to show the actual mechanism. But you think about some of the stabilization of why an acid is actually stable is because of that resonance structure. But that doesn't progress us to the reaction or to the product. But yeah, it can go up there, and most of the time it is going up there. But if I want to proceed to product, I would do this movement. And it can only happen if I have something for those electrons to be neutral in the next step. Now, I have lost a CO2. Now, I didn't write, sorry, minus CO2 at that step. That's not the full reaction, okay? And that, I wrote it over here, okay? But what we have to do now is, and if you take an inventory, that needs to be a ketone, and that needs to pick up a proton, so base forms alpha ketoglutarate. Well, that's a name. Okay. Alpha ketoglutarate. All right. The next reaction has alpha ketoglutarate, NAD plus, CoA, makes succinyl-CoA, CO2, and NADH. There are a couple of cofactors that are part of this also. FAD, TPP, and lipamide. The enzyme's name is alpha ketoglutarate dehydrogenase complex. Okay. This is exactly like the pyruvate dehydrogenase complex. Because this happens, I can write pyruvate like that. Oops, like this. Do you see how similar those structures are? It's just that R group. And the product would have been acetyl-CoA, where that is CH3. The exact same 3 type of enzymes to make the complex with the exact mechanism with TPP does this exact reaction. I won't make you draw that out because that's a long mechanism, okay? And much, much larger an issue for anything that I would ask you on the exam in terms of drawing mechanisms, which I'm not even going to ask you to draw a mechanism, okay? But I would want you to know each of the cofactors and what they do in the mechanism. Oh, wait. I've also gotten rid of CO2. All right. Succinyl-CoA, all right, to an intermediate, okay. And what's really interesting is that I totally forgot one substrate. Okay, check this out. There is roaming around in the body a phosphate, just a lonely phosphate. Okay, and we go to the product. All right, succinate-CoA synthase. And so what is going to happen here is one of these electron pairs will act as a nucleophile. I will attack, I will kick up, I will kick down, and I will pick up a proton, and the CoA leaves, and I have a phosphate on the organic intermediate. Now, what is interesting in this reaction that you probably should understand? I have just added a phosphate to an organic structure without breaking what? ATP. Most of the time it costs us energy to add a phosphate to an organic molecule. we've actually gained some energy in this reaction. All right? Now, I wrote this weird. I want you to understand what this next reactant is. I could have wrote this as GDP. Okay? So I have GMP, monophosphate, plus one more phosphate makes diphosphate. Okay? I'm just being lazy. I'm sorry. All right. What is the leaving group? GTP. Now watch this. The phosphate of the diphosphate will attack that phosphate. I kick up, I kick down, and I kick out. I have just made an energy molecule. Okay? The GTP can transfer its phosphate to ADP, the diphosphate, to make ATP without any loss of energy. And so most people will equate this particular reaction as making an additional ATP. Okay, so a lot of calculations when you look at things considers this ATP. Then I get this molecule here, which might not look like this, but it is an actuality that, because I have an acid, a methylene, and what comes off is an acid. An acid, a methylene, and a methylene. What's that? No, that means it's important. Okay. Tell me something about this molecule that you see. Symmetry. Okay. Once the succinate comes out of this enzyme, it is symmetrical. That means when it goes into the next enzyme, it can orient one way or the other. Okay? This is important. Okay? This might be a little bit important on places that you get graded, like a quiz or an exam. Okay? So, keep this in mind. This is symmetrical. Now, in this particular reaction, what really happens, I'm actually going to show you what really happens, the actual reaction of the entity where the phosphate comes in and reacts was exactly how I showed you. CoA falls off. But the next reaction actually has the enzyme as part of the reaction. And the nitrogen of a histidine will attack the phosphorus. And the artist did not study organic chemistry. We kick up and kick down, and the succinate falls off. The phosphate is transferred to the enzyme for just a little while, and then the GDP comes in, and I kick up and I kick down, and GTP falls off. So this actually has just a slightly different mechanism because of the enzyme itself. All right? When the reaction occurs between succinate and fumarate, okay, the reaction of a dehydrogenase is deprotonate and a hydride. Okay? So, which of these hydrogens do I deprotonate? They are all equivalent. They are also fit in the enzyme upside down. Okay? So if I was ever numbering them, 1, 2, 3, 4, right here, 50% of the time this would be 1, and 50% that would be 4. This would be 50% 1 and 50% 4. This would be a 2 and a 3. This would be a 2 and a 3, 50% of the time. All right? Mechanistically, and this is the last one we will do, I will take any one of those, fall down, and the hydride is accepted. And I get fumarate again, which is still symmetrical. We are almost done with the citric acid cycle reactions, which we'll finish next time. But then we'll talk about the importance of what that symmetry has and why it's important. And you will interact with that in a quiz. All right? No, I'll assign the quiz for you to do. I have very rarely ever do a quiz in class. I tend to want to do this with a quiz. Give you guys the quiz. Sometimes they are difficult or long, and I want you to work together so that you can learn. Not copy, but learn from each other, okay? Because I want you to try something and then try to convince somebody you're right, and they'll try to convince you they're right, and someone's going to be right, and hopefully you learn in that process.